Welcome to the 2017 AMATIC webinar series. Today we have a special treat. We've got Beyond Newton and Leibniz, the Making of Modern Calculus with Tony Piccolino. This presentation is sponsored by the Mathematics Intensive Committee. Please note that the views expressed by the presenter are not necessarily the views of AMATIC. Commercial products mentioned by presenters are not endorsed by AMATIC. Our webinar series this year is sponsored by McGraw-Hill. Thank you very much. And I just would have a brief biography for Tony. Tony Piccolino is a professor of mathematics at Palm Beach State College in Palm Beach Gardens, Florida since 2009. He also serves as faculty advisor to the Alpha Gamma Sigma chapter of Pi Theta Kappa. Prior to his tenure at Palm Beach State, he taught undergraduate, graduate, and doctoral courses in mathematics and mathematics education for 17 years at Montclair State University in New Jersey and served on several dissertation committees. In addition to his years in higher education, he also served for 25 years as a mathematics teacher and supervisor in public schools in New York State. Tony's educational background includes a BS in mathematics from Iona College, master's degrees from Yeshiva University and Fordham University, and a doctorate in mathematics education from Columbia University. Tony has served as president of the Association of Mathematics Teachers of New York, as president of New York State Supervisors of Mathematics, vice president for the National Council of Supervisors of Mathematics, and has served on numerous committees for the National Council of Teachers of Mathematics. For 20 years, he served as a consultant in AP Mathematics for the College Board as a reader for the AP Calculus and Statistics exams. Currently, in addition to serving on the editorial panel for the Mathematic Educator, he is a frequent presenter at AMATIC conferences, which is how we found out about him, by the way, and is a member of the Math Intensive Committee, the sponsor of the webinar today, the Statistics Committee, the Teacher Preparation Committee, and has served on the writing team for the forthcoming revision of Beyond Crossroads. Tony's research interests are in history of mathematics with the emphasis on reform in algebra in Victorian Britain and the rigorization of analysis in the 19th century. Welcome, Tony. We're going to go ahead and turn it over to you at this point.
Okay, I'm going to switch over.
All right.
And there we are. I think that's visible
perfect
to everyone. Okay, great. Well, thank you very much, Julie, for the introduction, and thank you, everyone, for attending the webinar today. I'm excited and honored to be able to do this. I enjoyed doing this presentation in Denver last fall, and calculus has been one of my favorite subjects to teach, and the history of it is a very rich history, and I'd like to share some of the exciting developments that took place in the 19th century. When we think about the development of calculus, of course, we often think about Isaac Newton and Leibniz, who are the co-inventors of calculus. But today, our focus is going to be on the making of modern calculus and what kinds of advances were made during the 19th century, because it was during that period of time when essentially what we see in calculus textbooks today was developed. Just for a little background information, if we go back to the 17th century, the problems that were of great interest to scientists and mathematicians at the time were problems that we generally deal with in calculus today, given a distance as a function of time, to find the velocity, acceleration, and the converse of that, finding tangent lines to curves, finding maximum and minimum values of a function, and finding the length of a curve, for example, the distance covered by a planet in a given interval of time. These were problems that were of great interest to scientists and mathematicians during the 1600s. The period of time just before Newton and Leibniz made their earth-shattering discoveries. And these are problems that we typically face in the classroom as teachers of calculus. There were many advances made in the early 17th century by various mathematicians. Newton and Leibniz were not the first. If we wanted to trace the seminal roots of calculus, we probably have to go back to ancient Greece and look at the work of Archimedes and Eudoxus and their contributions. But In the early 17th century, there were a number of mathematicians who preceded Newton and Leibniz. Gilles, Roberval, Pierre de Fermat, René Descartes, and Isaac Barrow. All of them dealt with problems that today are very familiar to us. The tangent line problem, the tangent line to a curve, is a very familiar problem in calculus. And each of these mathematicians made contributions to finding the tangent line to a curve. And they all approached this problem in a very geometric way. Johann Kepler, famous for his work with planetary motion, also did work in calculus, finding areas, volumes, and centers of gravity, and the lengths of curves. Galileo, as we know, did a lot of work with motion problems, and Galileo was actually a pioneer in developing some of the groundbreaking work with infinite sets, which didn't take place until much later on in the latter part of the 19th century by George Cantor. But Galileo did a lot of work with infinite sets, much earlier. And then there was Bonaventure Cavalieri, who developed his method of indivisibles, and then John Wallis, who did a lot of work with tangent lines also and other areas of mathematics. So you can see from this slide that a good number of mathematicians made significant inroads into calculus prior to Newton and Leibniz. And then, of course, the co-founders, or the co-inventors, I should say, of calculus, Isaac Newton and Gottfried Leibniz. Some people pronounce his name Leibniz. Leibniz was a German mathematician. He and Newton both developed calculus separately, although each accused the other of plagiarism. And as a result, there was a great deal of animosity between the two of them for the rest of their lives. Leibniz died in 1716, and Newton died 11 years later. And beyond the times that they lived, British mathematicians and European mathematicians basically didn't want much to do with each other. So when you look at the history of mathematics during the 1700s, you'll see relatively few contributions by British mathematicians, because they basically cut themselves off from the European mathematicians at the time. And it wasn't until the early 19th century, around 1815, when mathematicians like George Peacock and Charles Babbage and William Herschel decided that was enough. It's about time that British mathematicians now reunite with the European mathematicians so that they could assume their rightful place in the history of mathematics. Newton developed his method of fluxions, and the problem with Newton's was that he was very careful about publishing. And in fact, he didn't publish, and his first publication regarding calculus wasn't until 1687 in his famous Principia Mathematica. Leibniz, on the other hand, he developed some of his early ideas about calculus around 1673-74, and then published in 1683. Well, needless to say, Newton thought that Leibniz had stolen some of his material when Leibniz visited London, and as a result of this, Newton and Leibniz pretty much had a rather controversial relationship over the next many years. Both Newton and Leibniz based their calculus, they both took different approaches, but they both based their calculus on algebraic concepts. This is different from the mathematicians I mentioned a few minutes ago. Prior to Newton and Leibniz, the calculus concepts that were developed were done pretty much from a geometric approach. And Newton and Leibniz were the first people to take a more algebraic approach to developing the concepts of calculus. Newton and Leibniz, for example, reduced area and volume problems to anti-differentiation, which previously were treated as summations in a geometric manner. Newton used infinitely small increments, uh, for an x and y as a means of determining the fluxions, which, by the way, fluxion is just another name for the derivatives. And Leibniz dealt with differentials. So today we see the notation we see in our calculus books is primarily that of Leibniz, and the methods are primarily those of Newton. So Newton and Leibniz both made significant contributions, and both are credited with developing the calculus. But then again, I go back to a statement that Newton made once to people who asked him about the many discoveries he made. And he said, I've made many of my discoveries because I've stood on the shoulders of giants. And he was referring to not only the ancient Greeks like Eudoxus and Archimedes, but also to people like Fermat and Descartes and Isaac Barrow, who was Newton's teacher. These are people who made contributions, and Newton built on that, and Leibniz also. Newton was very free in using series to represent functions. Leibniz used what we today call the closed form with a formula. But our main thrust in this webinar today is to talk a little bit about what took place in the 19th century, the making of modern calculus. How did the calculus that we see in textbooks today, how did that come about? The 19th century has often been referred to as the age of rigor. During this period of time in the 19th century, think about all the different advances that were made. The discovery of various forms of non-Euclidean geometry, which separated geometry from the traditional Euclidean approach. Then there was the liberation of algebra, the development of non-commutative algebras, non-associative algebras, the development of group theory and ring theory. All of this algebra, this what we today call modern algebra, was developed during the 19th century. And the same is true for analysis. In the 19th century, mathematicians became concerned with putting calculus, the field of analysis, on a more rigorous foundation. And when we think about rigorizing calculus, it was more than just revising some basic concepts and cleaning up proofs of theorems. It went much farther than that. The rigorization process that took place in calculus during the 19th century actually produced new areas of mathematics. Mathematicians began to talk about things like uniform continuity, uniform convergence, completeness. All of these topics, all these concepts led into the development of different areas of mathematics which before had not been discovered, things like point set topology, which formed the underpinnings of modern analysis. So it wasn't just going back and cleaning up things that mathematicians in the 17th and 18th century had done, but the rigorization of calculus in the 19th century actually helped develop whole new branches of mathematics. So today, not only topology, but when we see courses taught at the undergraduate level and graduate level, like real analysis, those are all outcomes of the 19th century rigorization process. So this was an exciting time in mathematics. But as important as rigor was, it wasn't the most important issue for mathematicians in the 19th century. They were still concerned primarily with extending what they already knew in the field of calculus, for example, and applying previously developed theories and taking them to a new level. But as they were doing this, they realized that they needed to put calculus on a firmer logical foundation. So the development of new technical theorems stimulated this growth in foundations. For example, Fourier series challenged the old views of what a function is, what an integral is, continuity, and convergence. Something else was taking place in the 19th century. More and more analysis was being taught in the schools, in the colleges, and teaching analysis required a full understanding and an elimination of vague concepts. So this motivated mathematicians to clarify their definitions. And as a result of clarifying their definitions, they were able to put mathematics on a more rigorous, or calculus especially, on a rigorous foundation. The emancipation of mathematics also from science up until the 1700s, including the 1700s, mathematics was tied to the hip, as they say, to science. But today, and now in the 19th century, we see that mathematics got its first emancipation from science. Mathematics became a science in its own right. So all of these different reasons contributed to the need to rigorize calculus in the 19th century. The emancipation of mathematics from science, the need to have clearer concepts in order to teach analysis in a much more effective way in the schools, and also to help mathematicians as they extended analysis beyond what was discovered in the late 1600s and the 1700s. In order to extend those concepts, they needed to have clearer understanding of the basic concepts of calculus. As I mentioned a few minutes ago, calculus was very closely tied to science. Mathematics in general was tied to science in the 18th century. And analysis in particular was tied very closely to theoretical physics. So the rules of analysis were validated by the success in physical situations. This is kind of interesting because when someone found a solution to a differential equation, if it meshed with something in physics, on science, if it meshed with some physical reality, then they knew, as far as they were concerned, this was a proof that their theory was correct. Now mathematicians started saying, well, we have to be able to prove things apart from physics. We just can't look at a physical situation and say, okay, because it satisfies the physical situation that we're dealing with, that's a proof that the theory is true. So that was an interesting departure from what mathematicians and scientists accepted in the 18th century. Going back again to what we mentioned earlier, in the 17th centuries, calculus analysis was based largely on geometry. In the 18th century, mathematicians tried to put analysis on an algebraic foundation. And then in the 19th century, they moved even farther away from that, and they try to put calculus and all of mathematics on a more rigorous foundation. In calculus, the goal was to put the rigorization of calculus tied to the arithmetization of analysis. What we mean by that is that mathematicians had to take the real number system and put it on a firmer foundation. We had to have a much clearer and much more precise definition of what a real number is and the properties of real numbers. This was something new to the 19th century. So that brings us now to the major themes of the 19th century: rigorizing analysis and rigorizing all mathematics. The first half of the century, of the 19th century, we have to give due credit to the French school of mathematics. The French mathematicians were the leading advocates of rigorization during the first half of the 19th century. In the second half of the 19th century, the German school, led by Carl Weiers, became dominant in terms of discoveries and contributions. The first half of the 19th century was led by various French mathematicians. The most notable one was Augustin Cauchy. We see Cauchy's name appear in many different places in mathematics, and Weiers was the leading analyst of the 19th century in Germany. Calculus, as today we think of four major themes in calculus. We think of the study of functions, the study of limits, derivatives and integrals. Calculus became the study of functions in the 1700s, in the 18th century, largely due to the work of people like Euler and Lagrange. It's interesting at this point to stop and think about how the various mathematicians of the period thought about functions, a little different from the way we think about it today. Euler had two definitions of a function. He thought a function was an analytic expression, a formula that contained constants and variables. Now, of course, to a large extent, that's true. Our students see analytic expressions every day, which represent functions. F of x equals 2x plus 5, 3x squared minus 7, whatever the case may be. And he also thought of a function as a variable that depends on another variable. Again, both of these are accurate, but today we think of a function in a broader sense. Lagrange pretty much held the same views as Euler in terms of a function. Cauchy, who came a little later on in the early 19th century, viewed functions exclusively in terms of variables depending on other variables. His most famous work, the CordellAnalyse, which was published in 1821, is really the Bible today for the rigorization of calculus. It's a wonderful book. I believe Springer Verlag publishes both the French and then the English translation of it, and it's really worth looking through it to see how Cauchy approached the different concepts. Fourier, Joseph Fourier, another great mathematician of the 19th century. Here was his definition of a function. He said a function f of x represents a succession of values of ordinates, each of which is arbitrary. That's interesting. An infinity of values being given to the abscissas x, there are an equal number of ordinates f of x. We do not suppose these ordinates to be subject to a common law, so they didn't have to have an equation. They succeed each other in any manner whatever, and each of them is given, as it were, a single quantity. So here's a definition of a function, but he's not limiting a function to a formula. He's just saying for each x, there's a y. YDarish Ray, who was a contemporary, his definition of a function is similar to that of Fourier. And today we basically see the definition of a function in that manner. We think of a function as a set of ordered pairs in which for each element of the domain, there's only one element in the range. But one of the problems with 19th century writing is that however mathematicians define functions, and they each had their own way of defining functions, mathematicians didn't always use the definition of a function that they conceived in developing their theories. So in developing their theories, they may use functions in a broader way than they originally defined it, which was kind of interesting that they didn't always stick to their original definition. 18th century mathematicians believed that a function must have an analytic formula. This is going back now to the 1700s. If it didn't have a formula, it wasn't a function. In the late 18th century, and here's where things began to change with Euler and Lagrange, they allowed to have functions that have a different expression in different domains. This is our first encounter with piecewise functions. Of course, we teach that quite a lot in calculus today, where a function could be defined in one way for x less than or equal to a number, and then defined in a different way for x greater than or equal to a number. And Euler and Lagrange were the first ones to allow functions to be defined using different expressions. And today we call them piecewise functions, where the functions defined differently over different domains. Euler and Lagrange used the word continuous, where the same expression and the word discontinuous at points where the function changed formula. Now, today, in the modern sense, we would say the entire function could be continuous. So they were not using the words exactly the way we use them today, a little differently from the way we use them today. By the beginning of the 19th century, mathematicians finally started realizing that not all the properties of algebraic functions could be extended to all functions, which raised questions about what was really meant by a function, what was meant by continuity, what's meant by differentiability and integrability. So now mathematicians were realizing that the algebraic functions that were very commonly used in the 18th century, now these properties of algebraic functions didn't always apply to other kinds of functions. Cauchy categorized functions either as explicit or implicit. But they're always represented by some equation or some expression. Cauchy also divided functions into simple functions and composite functions. Today we realize how important composite functions play a role in our teaching and learning of calculus. Many of Cauchy's proofs and his concepts did not rely on analytic expressions. So that's interesting. He insisted on an analytic expression in the definition of functions, but when you start to do his proofs, he didn't rely on a function having necessarily having an analytic expression. And the textbooks in the early 19th century, as we said, had varying definitions of a function. And again, going back to what I mentioned a few minutes ago, often deduced theorems which didn't follow from the definition of a function. So they define functions one way and then maybe used a different definition in deducing theorems from, based on the concept of function. Okay, let's talk a little bit about some of the people who made some major contributions. One person who doesn't get very much credit is a Jesuit priest by the name of Bernhard Bolzano. Bolzano was a Jesuit priest, a philosopher, a mathematician from Bohemia, and his work pretty much went unnoticed for about 50 years. And his initial motivation, he really wasn't interested initially in reforming calculus. His initial concern was trying to find a purely arithmetical proof of the fundamental theorem of algebra. The fundamental theorem of algebra was first proven by Gauss as part of his doctoral dissertation back in 1796. And then Bolzano, a number of years later, around 1816, 1815, 1816, was interested in looking for a purely arithmetical proof of the fundamental theorem of algebra. But Bolzano then drifted over into analysis, and a couple things about Bolzano's work. First of all, he denied the existence of infinitely small numbers, which were called infinitesimals, and infinitely large numbers. This is the definition he gave in 1817 of continuity. He said, and actually the definition that you see on the screen is not what you see in the textbook, but it's essentially equivalent to that. A function f of x is continuous in an interval if at any x in the interval, the difference f of x plus w minus f of x can be made as small as one wishes by taking w sufficiently small. If we analyze this definition, it's pretty much equivalent to the way we define continuity today. Today we say a function f of x is continuous at a point c if the function is defined at c, if the limit as x approaches c from both sides is equal, exists, and third, that the limit and the function value are the same. Although he didn't quite say it that way, this definition is equivalent to that. So he gave probably the earliest proper definition of continuity. He was the first one to define the derivative of f of x as a ratio. Today we say the definition of the derivative is the limit of the difference quotient f of x plus delta x minus f of x over delta x. So he was the first one to define a derivative. Again, not quite the way we see it in the textbooks today, but the same concept of using the difference quotient and letting the delta x approach 0. Most mathematicians in the early 19th century believed, and they thought they proved, that a continuous function must be differentiable except at isolated points. And for the most part, we, the examples we use in class are pretty much like that. However, Bolzano recognized that a function could be continuous at every point and never have a derivative. And in 1834, he gave an example of that, but he didn't publish it. So as a result, he doesn't get credit for it. The person who actually gets credit for that is Weiers, coming up in a few minutes. But Bolzano recognized early on that a function could be continuous at every point and non-differentiable at any of those points. I happened to be discussing this with my calculus class today. We were talking about the theorem: if a function is differentiable at a point, then it's continuous at the point. And then I brought up this this example or this notion of Bolzano finding an example. They wanted me to graph it on the graphing calculator, and I said, no, I can't do that. But in any case, Bolzano understood that there was a distinction between continuity and differentiability. He understood it well enough to know that you could have a function that's continuous at every point and non-differentiable at any of those points. Since functions did not have an analytic expression, it would not have been acceptable for mathematicians of that era to work with them. Again, mathematicians were still tied to the idea that in order for a function to, in order to work with functions, it had to have some kind of analytic definition. Bolzano also proved the intermediate value theorem, although there's some controversy about that. On a later slide, Cauchy also proved the intermediate value theorem. Again, there's always these controversies that come up in mathematics because sometimes mathematicians don't necessarily publish what they prove, and then later on somebody else proves it, and then there's always that controversy about who had priority. And in this case, this is one of those theorems, like so many in mathematics, that two people could have worked on them independently. Nobody plagiarized from anybody else. But in this case, Bolzano had a proof of the intermediate value theorem. Cauchy claimed he had one also. Interestingly enough, in 1851, after Bolzano had died, a work was published by him on paradoxes of the infinite. And in this work, he anticipated much of what George Cantor did about 23 years later. In 1873, George Cantor published some of his groundbreaking work on infinite sets, which met with a lot of controversy from the mathematical community, where he talked about sets being equivalent to a proper subset of themselves, and George Cantor ran into problems with his mentor, Leopold Kronecker, to the point where George Cantor actually had a nervous breakdown and spent most of the rest of his life from the 1870s until 1918 when he died. He spent most of his life in a mental institution, having felt the rejection from many people in the mathematical community about his theory of infinite sets. But Bolzano had already laid some of the groundwork back in 1851. Again, this was published after he had died. The premier mathematician, at least in terms of rigorization of calculus, would be Auguste Cauchy and then Karl Weierstrass. Auguste Cauchy was the best French mathematician of the 19th century, the leading mathematician. These are his three great works. And in these three great works, he set the pace for the rigorization of analysis. His definitions of basic calculus concept are very wordy. We're going to look at the definition of a limit in just a moment. They were wordy, they were vague, they were non-rigorous, meaning that they didn't have epsilons and deltas in them and quantifiers and all the things that you see today, but they were correct, and they were a first step in the rigorization of calculus. Now, why would we give Cauchy that much credit for the rigorization of calculus if his definitions were vague and wordy and so on? Actually, his proofs, he made up for it in his proofs. His proofs were very rigorous. His definitions tended not to be. They were correct, but not they were not rigorous by today's standards, but he made up for it in his proof. And he was the first one, like I said, to give a comprehensive treatment and analysis based on a precise definition of limits. Again, not the epsilon delta definition that you see in the textbooks today. That's due to Weierstrass. But here's Cauchy's definition. When the successive values attributed to a variable approach indefinitely a fixed value so as to end by differing from it by as little as one wishes, just that to end is a little bothersome. This last fixed value is called the limit of all the others. Thus, for example, an irrational number is the limit of diverse fractions which furnish more and more approximate values of it. Now, again, we probably wouldn't consider this to be rigorous today, but it has all the ingredients of a precise definition in mathematics. He just didn't polish it up the way Weierstrass did later on. But then when you look at his proofs are very rigorous. In a traditional sense, infinitesimals were considered to be infinitely small fixed numbers. Cauchy defined an infinitesimal to be a variable with zero as its limits. And this is his wording and definition. One says that a variable quantity becomes infinitely small when its numerical value decreases indefinitely in such a way as to converge towards the value of zero. That was Cauchy's definition of an infinitesimal. Infinitesimals were used in a very limited way and imprecise way by people like Newton and Leibniz, and mathematicians have followed beyond that. Cauchy was the first one to give a definition, a more precise definition. Prior to Cauchy, different expositions of the calculus adopted the differential as the fundamental concept. In fact, the way derivatives were introduced previously, derivatives were introduced as the differential coefficient in the expression dy equals f prime of x dx. When we introduced differentials in our calculus class, we defined differential y to be the derivative of the function times differential x. Well, that's how derivatives were introduced prior to Cauchy. But Cauchy viewed the derivative as the limit of the difference quotient, pretty much like Bolzano had done. And Cauchy gave it a precise definition, the definition that we typically see in calculus books today. Cauchy's the person who's credited with introducing the chain rule to find the derivative of the composition of functions. And some of the major features of Cauchy's work that set the pace for other mathematicians that followed. He gave an explicit formulation of continuity and differentiability in terms of limits. Now remember, Bolzano had given a pretty nice definition of continuity, but now Cauchy cleaned it up a little bit and put it in terms of limits. The same thing with differentiability. Cauchy also made the mean value theorem a very important theorem. It was previously known to Lagrange, but Cauchy is the one that gave the mean value theorem a prime role in the development of differential calculus. His definition of the definite integral and proof of the fundamental theorems, those are due to him. Basically, during the 18th century, the integral was generally viewed as the inverse of the derivative. but Cauchy now took the definite integral and developed the fundamental theorem calculus in terms of the limit of Riemann sums and the things that, again, we typically teach our students in our Calculus 1 course. And now we come to the other mathematician, the other great contributor to the rigorization of calculus. And it's really difficult to just limit it to one or two people. But again, Cauchy and Weiers have to be considered to be the prime movers in the rigorization of calculus. Weiers is probably the most famous German mathematician in the 19th century, especially during the second half of the 19th century. We mentioned earlier that the calculus of Newton and Leibniz was primarily a calculus involving geometric variables associated with geometric curves. Euler-Lagrange tried to substitute the principles of arithmetic into the foundations, but they were only partially successful. Their approach was pretty much algebraic. But Weierstrass was one of the first mathematicians in the 19th century to recognize the need to put the real number system on a strict logical foundation. And that was one of his major contributions, is contributing to contribute to the rigorization of calculus. He recognized that you first have to put the real numbers on a strong and rigorous foundation. Richard Dedekind also was one of the pioneers in the rigorization of the real number system. I'm not sure how this came out on the slide, but he proved that, or he claimed that the square root of 2 times the square root of 3 equal to square root of 2 times 3 had never rigorously been proved. So both Dedekind and Weierstrass recognized that a lot of the work with radicals had never been given a rigorous approach. Weierstrass was the first one to give a rigorous construction of the real number system, and that set the pace for today what we call the modern rigorization of calculus. So today, beyond our Calculus 1 class, when we see concepts in advanced calculus or a course in real analysis, the concepts that we see in those courses, those are basically the work of people like Weierstrass and Dedekind and Kronecker and other people. Kronecker, let me just back up here. I think I lost one of, nope. Just bear with me for a moment while we get to back here. Weierstrass is the first one to give what we call a precise definition with all the bells and whistles. Here's the definition that we typically would see in a calculus textbook, the epsilon, the famous epsilon delta definition of a limit. That's due to Weierstrass. Weierstrass was also credited with a very famous theorem in real analysis called the Bolzano-Weierstrass theorem. Every bounded monotonic sequence is convergent. The proof of that you see in a real analysis course. That's not something we typically would do in Calc 1 or Calc 2. Bolzano, we mentioned earlier, had discovered that you could have a function that's continuous at every point, but is nowhere differentiable. Weierstrass found a function which is everywhere continuous, but nowhere differentiable. And here's an example of a function. So we have f of x equals the sum from n equals 0 to infinity of b to the n cosine of a to the n times pi of x. Weierstrass gave this example, and like I said, he was the first person to put calculus on a rigorous foundation. Now, Weierstrass also, I want to mention a person who's a great contributor to calculus in the 19th century, and that's the famous Russian woman mathematician named Sonia Kovalevsky. Sonia Kovalevsky unfortunately died at a very young age. She was 41 when she passed away. Kovalevsky at the time was not permitted, as the Russian custom went, to do graduate study and certainly go for a doctoral degree in Russia. She went into an arranged marriage so that she could leave the country and study for her advanced degree abroad. She came into contact with Karl Weierstrass, who, by the way, was not the easiest person to get along with. But Weierstrass recognized the genius of Kowalewski and took her under his wings, and he was her doctoral sponsor, her doctoral dissertation sponsor. And Kowalewski did all her did a lot of her initial research under the auspices of Weierstrass' tutelage, and then excuse me, Kowalewski made many great contributions in mathematics and physics, especially in the area of differential equations. So I want to be sure that we mentioned that although Kowalewski wasn't directly involved with the rigorization of calculus, but because of her association with Weierstrass, she was able to make great contributions and significant contributions in the field of differential equations, in the development of various kinds of existence theorems in differential equations. I'm going to stop here because I'm looking at the time, and I know that Julie, I think we are allowed for some time for some questions.
Yes, we did. I haven't had any come in.
Okay.
I know.
Okay.
I don't know if you have anything else, if you wanted to finish up, but no questions have come in at this point. So we have a few more minutes. I only need about 5 at the end to wrap up if there are no questions.
Well, I think, from a teaching point of view, and I think this is, we can go on with the history because the history of calculus is so rich, and there are several resources I could recommend. There's one it's an old resource, but it's still, as they say, an oldie but a goodie. Carl Boyer, the famous historian of mathematics, wrote a book on the history of calculus and its conceptual development. It's still available in paperback. You can get it from Dover Publications. This is not a commercial, but I just wanted you to know that it's still a classic. So many of the history of math books today do a wonderful job with that. There are many other books. If anybody's interested, I'll be glad to send them. If you just shoot me an email, I'll be glad to send you a whole list of references of books that you may want to use for your own professional development. In terms of getting material on the history of calculus. But what I wanted to say in terms of pedagogical value, students are always interested in the history. I mean, sometimes students will say, well, why do we have to learn the history? But it enriches mathematics. It helps students to understand that even a subject that at first may seem very dull to them has a very rich history and rich personalities. Students are fascinated by the controversy that existed between and the animosity that existed between Newton and Leibniz, and how each one accused the other. And not only was it a controversy between two individuals, but this controversy went beyond. It had nationalistic implications. People in Europe, the European mathematicians, were separated. I mean, the British mathematicians basically divorced themselves from the European mathematicians for about 125 years. That seems incredible. But from about the early 1700s up until around 1825, British mathematics was pretty much on its own, didn't have very much to do with the rest of European mathematics. And if you look at history books in the 1700s, you'll see names like Brooke Taylor and Colin Maclaurin, the Maclaurin series, the Taylor series. You'll see a few names, but the bulk of mathematical development during the 18th century came from places other than Great Britain. On the other hand, once the British mathematicians reunited themselves with the rest of Europe in the 19th century, the British mathematicians made very significant contributions. When you look at all the great work in matrix theory and modern other areas of modern algebra with Arthur Cayley, George Peacock, Augustus de Morgan, all of these were, British mathematicians. So it's interesting how a little controversy that between two individuals could set off two schools of, two camps, so to speak. The other thing is that students like to hear about enriching stories. The old story about L'Hopital's rule having been discovered by one of the Bernoulli mathematicians, one of the Bernoulli brothers. And then Bernoulli had gotten into a agreement with L'Hopital. L'Hopital was a very wealthy French mathematician, and L'Hopital asked Bernoulli to share any of his discoveries with him, and L'Hopital agreed to give Bernoulli a pension for life. He was very wealthy, and Bernoulli had just gotten married, was without a job. This was around 1692. He agreed to that, and during the course of 1692 to 1696, those years of correspondence, he shared many of his discoveries with L'Hopital. And then L'Hopital published his famous calculus book, supposedly the first calculus textbook in 1696, and didn't give any credit to Bernoulli. And then when L'Hopital died in 1704, Bernoulli came forward, and everybody said, yeah, that's easy for you to say because L'Hopital is now dead. But in 1922, they discovered letters of correspondence between Bernoulli and L'Hopital that had not been previously discovered, and they found beyond a shadow of a doubt that this was exactly the case. L'Hopital's rule is a discovery of Bernoulli, and students like stories like that. And the history of calculus is so rich, and there are just so many different stories that one could share. So I encourage you to to incorporate the history of calculus into your classes, and I think you'll find that the students will be enriched by that. And again, I will be happy to send a list of references to anyone that's interested in that. There are several good books and references that could help you incorporate the material into your classes as different topics come up throughout the calculus class. And I just want to take this opportunity to thank everybody very much. It's been a great privilege to be able to do the webinar. And I look forward to seeing many of you in San Diego for our AMATIC conference this year. So thank you again. And Julie, I'll turn it over to you.
Yeah, you did have one question that came in, and it was almost a perfect segue of what you just were talking about. It was, could you share a favorite example of how you integrate historical aspects of calculus into the Calc 1 curriculum?
Well, I like to start with problems. For example, at the beginning of the course, I'd like to spend some time on the first day of class trying to get students to understand why are we even studying calculus? What kinds of problems can we study? And I'll go back to a very simple problem like the problem of finding areas. Now, students come into our class and they know how to find areas of triangles and squares and rectangles and parallelograms and so on. And the ancient Greeks knew how to find those areas also. But how do they find the area of a circle? Well, I try to share with them, and I kind of sketch out how Eudoxus and Archimedes, in particular Eudoxus, how he approached the problem. He inscribed a triangle, and then he found the area, of course, and then he inscribed a quadrilateral, and then a pentagon. And as he increased the number of sides, the area of the polygon gets closer and closer to the area of the circle. Actually, I also do this again when I get to chapter 4, I'm introducing the integral, and we're introducing Riemann sums. But before we even get to that, how did the ancient Greeks approach this this concept of finding the area of a figure that they don't know how to get, other than triangles and squares and rectangles and so on? So I try to use the method of exhaustion. Sometimes the mathematicians got exhausted by doing that, but the method of exhaustion, as the name goes, was a method that was very commonly used by mathematicians like Eudoxus and Archimedes to find areas of regions that they couldn't find by other means.
Perfect. Thank you so much. There are tons of thank yous coming in the chat window. You guys can certainly thank Tony there as well. I will send him that log, so if you had other questions for him, you can put them there as well. I'm going to go ahead and wrap up my part of the webinar here, which is just to remind you of a few things. I want to thank everyone for joining us today, and again, thank you, Tony, so much. I think I could listen to you talk about math history all day. You make it very exciting and very engaging. Check us out on social media for AMATIC. We are on Facebook, and we are also on Twitter. Recordings of past webinars can be found at bit.ly/amatic-webinars. It usually takes me about a week or two to make sure that I get everything uploaded and we get this archive ready for you. Please, 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 please take 2 minutes to evaluate the content of the webinar and the presenter. If you go to bit.ly /amatic62. If you do need a confirmation that you were here today, you have to do that because that's the only way that I can get you that certificate. And I think if I don't have a, oh, I have a copy paste fail. I have Tony's email address, not the, I went to go copy paste and I thought I had that survey in there and I did not. I had your address instead. So let me type it in there for them. It just takes a few minutes to do. It looks like you're going to have to highlight that I didn't take it as a hyperlink, but bit.ly /amatic62. So we just keep adding on to those surveys. I will send an email after the webinar when we have everything produced. And you guys will know when everything is up online. I'm going to go ahead and stop the recording now.